For any assignment-related queries, call us at +1 678 648 4277. You can mail us at info@architectureassignmenthelp.com or reach us at https://www.architectureassignmenthelp.com. Architecture Assignment Help. 250. An inventor proposes a refrigerator that makes ice, which is then melted and used to cool a cold storage room. The refrigerator is put into a closed insulated room without any airflow into or out of the room. It is turned on when the water is liquid at 0 C, the initial room temperature. It makes 10 kilograms of ice, which is then melted to liquid at 0 C without any evaporation of the water. A. Will the room temperature increase or decrease for the entire process, from the time the refrigerator is turned on to the time the ice has melted? B. If the refrigerator has a COP of 3 and it is only used to make the ice, how much electrical energy does the refrigerator require? Take the internal energy change from ice to liquid water at 0 C as 334 kJ/kg. The COP is the rate of useful cooling to the rate of electrical energy consumed. C. If 0.25 kilograms of water evaporates after all of the ice has melted, does the room temperature increase or decrease over the entire process? Solution. A. For a system composed of the room plus the refrigerator and water/ice, the net change of the internal energy of the water to ice and back to water is 0. The refrigerator operates in a cycle, so there isn't any energy change. There is only a flow of electricity into the room, an energy gain, so the room temperature will increase. B. COP equals col/WLEC equals col/COP is equal to 10 times 334/3 equals 1113 kJ, which is the net energy flow into the room. C. In this case, the final state of the water has a higher internal energy of 0.25 times 2375 is equal to 594 kJ. This is less than the electrical energy, so the room temperature still rises. An MIT fraternity holds a party in their largest common room, which is 10 m long x 10 m wide x 3 m high. The party lasts 4 hours and 300 students attend. Because everyone is dancing, each person gives off 300 BTU/HR of sensible heat. The home theater system uses 1000 W. 2 100 W lights are also on. The room has a 0.1 m concrete slab floor. The air in the space and the slab are initially at 68 degrees Fahrenheit. Assume that the specific humidity remains constant for both problems. A. If the room is perfectly insulated and there is no ventilation system, what is the temperature of the air in the space at the end of the party? Assume that the air and floor slab end up at the same temperature and that all electrical equipment is on the whole time. Is this a comfortable temperature? B. For their second party, the frat brothers decide to naturally ventilate the space using 2 windows, each 1.5 m x 2 m. The temperature of the air outside is 60 degrees Fahrenheit and the wind velocity is 2 m/s. Let Vin be the velocity of air entering the open windows. Assume that Vin equals 0.35 wind and that all the rate of air leaving the space is the same as air entering the same. If all other conditions stay the same, what is the temperature of the air in the space at the end of the second party? Again, assume that the air and floor slab end up at the same temperature and that all air is well mixed. Is this a comfortable temperature? Solution. First, find the total amount of heat gain in the room. To find final, we use the energy conservation equation. Increment where plus increment slab equals care mere increment T plus slab increment T equals total. We have seen from previous problems that in this situation we can assume that increment where will be negligible, so we will only consider increment slab. We know that slab equals 880 J/kgk, slab equals 2,100 kilograms per cubic meter, and slab equals 100 square meters x 0.1 m equals 10 cubic meters. Plugging these into the energy conservation equation, we find. Clearly, this is not a comfortable temperature for the party. B. We know that the total amount of heat gain in the room will be the same as in part A. For this problem, it is easier to use the rate of heat gain in W. We can also find the rate of internal energy change in the slab. dslab/dt equals 880 J/kgk asterisk 2100 kg/m3 asterisk 10 m3 increment T / for HRS 3600 S/HR equals 1283 asterisk increment TW. Now find the mass flow rate of the air. Consider the energy conservation equation with the addition of moving air into the space. Since we know that the rate of air entering the space is equal to that leaving, we can simplify. 2. Plugging everything in, we solve. This is clearly a much more comfortable temperature for the party.